to pick up where we left off in our last class. What we're going to do is we're going to start talking a little bit more about the treatment of numerical data. We had already talked about unit conversions, and we said that unit conversions are kind of a necessary process in chemistry because um, there are a number of different units that get used to describe any given property. And we said that there were a set of units that were kind of special in that they could be applied directly to the metric system, which allows us to put prefixes onto those unit names and then treat them as multipliers for the data. So, for example, we said that there were 100 centimeters in 1 meter. Actually, let's just keep that as just an M. Okay, so we knew then that we could calculate the number of meters in a given number of centimeters. So let's say we had, 350 centimeters. Okay, we need a conversion factor that will allow us to do this calculation. And we said that we can derive a conversion factor from the equivalency that's given to us in the conversion. In fact, we would always be able to come up with two of them. Oops. Okay. One would allow us to convert from centimeters to meters, and the other one would allow us to convert from meters to centimeters. Which one do we use? Well, the best way to remember it is that you want to choose the conversion factor where the units that you want are on the top. So here we're starting off with 350 centimeters, and we want to convert this to meters, so that means the meters need to be on top. So we have 1 meter on top and 100 centimeters on the bottom. Okay, so now when we look at this, we're going to be dividing 350 by 100. Okay, and this gives us 3.50 meters, and that's our answer. And likewise, we could do the conversion in the other direction. So if I had, say, 5.68 meters, and I want to convert that to centimeters, I would use the other version of the conversion factor, which puts the units that we want on top, which is the 100 centimeters, divided by 1 meter. And what we wind up with here is 568 centimeters. And we can convert any number of units using this exact same method. So for example, if you wanted to go from liters to gallons, all you would have to do is recognize that 3.8 liters equals 1 gallon. How would you know that? Well, you can always look that up. Okay, it'll be in your textbook, it would be on an equation sheet, or you can just look it up on the internet. Another one that's pretty common is the 2.54 centimeters is equal to 1 inch. Okay, again, any possible unit conversion you can imagine is going to operate the same way. We just got to use these equivalencies to come up with conversion factors. Okay, so just like we saw before, there's 2 different conversion factors that can be derived from each one. And choosing the right one is simply a matter of making sure that the units that you want are on the top of the fraction. And that's it. Now, not all unit conversions are necessarily going to be this simple. There are some units that are not related to each other in this way, most notably units of temperature. Okay, there are three different units of temperature that we concern ourselves with in chemistry. We have the Fahrenheit scale, the Celsius scale, and the Kelvin scale. Now you may be asking yourself, why are there so many different scales here? Well, there's actually a pretty good explanation for it. You see, back in the old days, chemists wanted to be able to record the temperature of their experiments because we knew that a lot of processes really depend upon what the temperature of the room is. So one thing that they had discovered is that if you took a glass tube and you put some liquid in there and then sealed off the edges, that if you increase the temperature, the level of that liquid would rise. And what they did was they basically had devised the first thermometer. Now, early thermometers were not as simple as the ones that we see today with just a simple glass tube. The glass tubes that they used back in the 16, 1700s were long windings of glass tubes. Okay, but still, it's the same premise. Now, the problem was, how do you describe or how do you relate the distance that the liquid travels to the actual temperature? Well, they decided that they would create a scale, and there would be two reference points, a low temperature reference point and a high temperature reference point, where both the reference points could be rather easily obtained in the laboratory and with a fair amount of accuracy. So one of the first scales, the Fahrenheit scale, okay, puts the upper reference point at 96 degrees and the lower one at 0 degrees. The 96 degrees corresponded to body temperature, and the 0 degree corresponded to a mixture of ice and water, which was the lowest temperature that they could reach in a laboratory. And literally, they marked these temperatures off onto the piece of glass that was containing the liquid, and then they just drew these evenly spaced divisions, degrees, if you will. Okay, so they would have these extending past the upper temperature and the lower reference temperature. Now, the problem with this was that these were not very reliable reference points. First of all, we know that the temperature of the body is not always going to be exactly the same now. Some people run a slightly warmer temperature than others. Not to mention the fact that it's not 96 degrees. It's 98.6 is the average value. The other problem was that the ice-water mixture, I said ice-water, I should have said ice and salt mixture. And when you put these together, depending upon what the ratios of the ice and the salt were, that can really affect what this lower temperature was. Now, somebody else came up with the idea of creating a scale with slightly more reliable reference points. Okay, which were 100 degrees Celsius and 0 degrees Celsius, and 100 corresponded to the boiling point of water, and 0 degrees corresponded to the freezing point of water, which is something I think could be measured much more reliably. Now, you'd think that that was enough and we'd be done, but we're not. You see, there's a problem with the Celsius scale too, and that is that just like the Fahrenheit scale, it's possible to have negative temperatures. The reason why this is a problem is because, as you're going to see later on, temperature is really a measure of how fast molecules are moving. Now, if we're talking about the speed of a molecule as a function of temperature, as temperature goes down, we would expect that the molecule would get slower and slower and slower, until eventually we get to a point where the molecule is not moving at all. Now, if we were to use the Celsius scale or the Fahrenheit scale, what we would find is that at negative temperatures, we would actually have negative motion of the molecules, less than no motion, which doesn't make any sense at all. So instead, we needed to have an absolute temperature scale, okay, that has an absolute bottom to it, which we called 0, and that's 0 Kelvin. And 0 Kelvin is the temperature at which all molecular motion ceases. Okay, and then we just have temperatures going up from there. Okay, so these are the three main scales that are used to describe temperature. Now, there's going to be times where we're going to be expected to be able to convert between them. Now, converting between the Celsius scale and the Kelvin scale is pretty straightforward. Okay, the temperature in Celsius is equal to the temperature in Kelvin minus 273. Okay, likewise, the temperature in Kelvin is equal to the temperature in Celsius plus 273. So again, that's a very straightforward conversion. Between Celsius and Fahrenheit, it's a little bit more work. Okay, the temperature in Fahrenheit is equal to 9/5 times the temperature in Celsius plus 32. Okay, which means if we want to convert from the temperature in from the temperature in Fahrenheit to the temperature in Celsius, we have to rewrite this equation. And we get 5/9 times the temperature in Fahrenheit minus 32. Okay. Now, in principle, I guess you could come up with an equation that relates Fahrenheit to Kelvin, but we just tend to do kind of a two-step conversion. So let's do that real quick. Let's say we want to convert, let's say, 300 Kelvin to degrees Fahrenheit. Well, the first thing we would have to do is to go from Kelvin to Celsius, and then from Celsius to Fahrenheit. Okay, so let's see here. We have the temperature in Celsius is equal to the temperature in Kelvin minus 273. Okay, which in this case is going to be equal to 300 minus 273, which, if I'm doing the math in my head correctly, and I don't always do that, should be equal to 27 degrees Celsius. Now, to go from there to Fahrenheit, the temperature in Fahrenheit is equal to 9/5 the temperature in Celsius plus 32, which equals 9/5 times 27 plus 32. And I am not going to trust myself to do that math in my head. So what we're going to do is do this in a calculator. 9 times 27 is 243 divided by 5 gives us 48.6 plus 32. That's 80.6 degrees Fahrenheit.